All right, guys, today we're going to talk real briefly about reactions of alkanes. This is sort of opening up our section on organic reactions. Now, remember that we're not going to go too massively deep into everything here, but we want to sort of get some basics of a few organic reactions and sort of know how they happen and talk a little bit about mechanisms and stuff so that, again, once you get into college, that you can get some, obviously, a lot greater detail on the things that we're just sort of introducing here in our class. So we're going to talk about alkanes. Now, what's important for us when we think about our alkanes is that, remember what an alkane is that we have a chain of carbons and it is completely saturated. And what that means for us is that there are hydrogens, as many hydrogens as we can fit on it are there. And since carbon forms 4 bonds, if it's not bonded to another carbon, then those other bonds are taken up by hydrogens. So all of those bonds, they're single bonds, they're all covalent bonds, and they're all non-polar bonds. And that's obviously going to lead into some of the properties of alkanes, and it's going to lead into how the reactions of alkanes are going to differ a little bit from the reactions we'll see for alkenes and alkynes later. So, first of the two types of reactions that we're going to talk about today are combustion reactions. And combustion reactions you probably remember from your Chem 1 classes. And one of the things that we said in Chem 1 classes was essentially that you had a hydrocarbon of some kind, that in the presence of oxygen, that you had some sort of initiation. And you see it down here at the bottom, it says you need an initiation step. Usually that is some sort of heat or spark or something like that. You got to light the flame, in other words. And that you always get the same two products. We always get these two products of CO2 and water. Okay? Now, that's, as many things you learn in Chem 1, that's mostly true. What makes that non-true is that this is true if we have excess oxygen. So if the O2 here is not our limiting reagent, if we have more than we need of that reactant, then this is what we get. We get pretty much clean burning, and we get carbon dioxide and water. Now, some people might dispute the clean burning now because carbon dioxide obviously is a greenhouse gas and leads to some issues there. But on the whole, I mean, these are relatively non-poisonous things that are coming out of here. So if we're in excess oxygen, then we've got a good clean reaction. This is what we call an oxidation reduction reaction. Now, that might not immediately ring a bell to you. But what that means is that we could go back and we could assign oxidation numbers to everything. And we're not going to go through that. But if you want to go back and watch a Chem 1 video, I think it's 6.3 where we talk about that. And we could assign oxidation numbers to all this stuff. And then we could tell what got oxidized, what got reduced, all of that sort of stuff. And that would indicate to us that it's an oxidation reduction reaction. Basically what that means is that some electrons are shifting from place to place here. And of course what's important to us as, modern human beings is that these reactions are extremely exothermic. This is like maybe one of the most important reactions as far as driving our society, because this is how we burn fossil fuels. So CH4 here is methane, that's natural gas. We're going to use that to heat our houses, and in some rare cases drive some vehicles. The liquid propane in your grill, that's another example of a combustion reaction. The gasoline you burn in the car, all of these are combustion of alkanes, and that's because they're really exothermic. They release a lot of energy when that happens. That energy can then be used, obviously, to heat things, but also to power and drive other things and get other things going as well. So that's combustion reactions. We said that we have to have sufficient oxygen, so that sort of begs the question, what happens if you don't have sufficient oxygen? Well, if you don't have sufficient oxygen, you tend to get some other products. So we can get carbon monoxide produced. We can get basically ash or carbon itself produced. We can get maybe some more dangerous things. We can get something like formaldehyde, which obviously is going to be dangerous, a carcinogenic substance. We can get things like acetic acid produced. You'll notice that all of these things are essentially taking the place of the carbon dioxide, and that's just if there's not enough oxygen for this reaction, then we start to get all kinds of other byproducts forming out of it. So if everything is running clean and you've got plenty of oxygen, the oxygen can get to the fuel chamber where it's being combusted, then we tend to have a lot less of that. But of course, it doesn't always work that way, and so we get carbon monoxide in the back of the car engine because you're not getting a complete combustion reaction. So remember some of those: carbon monoxide, carbon ash, formaldehyde, acetic acid, all of those are some possibles, and there's a lot of other possibles, but those are some of the biggies that we want to remember. So our second type of reaction are halogenation reactions. Halogenation reactions, basically that means that we're going to add chlorine or bromine to an alkane. And the alkane, remember, could be just about anything. Remember that when you see an R, that just means some long chain of carbon, and how long it is sort of varies. So to do that, we're going to add a halogen to it. Now remember, and again from Chem 1, hopefully you remember that halogens are diatomic. So if we add a chlorine or a bromine to it, it's not just you're adding one. There's a Cl2 there that's going into it, and that's obviously going to, we're going to break that apart, and we're going to add one of those to the alkane, and that's going to be our halogenation reaction. If we add one of them, that's what we would call a monohalogenation, or in the case of this one, a monochlorination. We could obviously have a monobromination if we're adding the bromine. And so what you'll see here is that the chlorine is going to break in two. One of them is going to add to the alkane. The other one is going to add to a hydrogen. We're going to get hydrogen chloride gas or hydrogen bromide as the other byproduct of that reaction. Now you'll notice here that it says in sunlight or with high temperatures. Man, it works really well when you underline stuff with a yellow background in yellow. In sunlight or high temperatures, alkanes will react with halogens. And essentially what that means is you have to have something to break this bond, and what breaks that bond is some sunlight or some high temperatures. That's going to help to break the bond in the halogens, and then we can get the reaction to actually occur. So if we wanted to say chlorinate methane, we wanted to add a chlorine to it and make it methyl chloride. I'm sorry, make it chloromethane. Probably should use the correct terminology here. Then we're going to get this product here, okay? And so again, it has to be excess halogens. If we get excess halogens, sorry, it doesn't have to be excess halogens. It's late, guys. It's midnight. If we have excess halogens, though, what we can do is we could continue to essentially add on to our brominated product or our chlorinated product. So right here, we have a monochlorination product, okay? And so we could then add on to that product, though. And so if we took that and there was more chlorine, okay, then we could have the next step where we get CH2, Cl2, okay, and then we could actually carry that on and go all the way, and we could get carbon tetrachloride, or if we just went the intermediate step there between that, we could get our good friend chloroform. And so if we keep adding those excess halogens, then we can keep replacing hydrogens. So how does this process happen? Well, this process happens via a mechanism called a free radical chain mechanism. Now, we haven't talked a whole lot about mechanisms. Mechanisms are super massively, amazingly important in organic chemistry, and you're going to learn a lot more about them in your college classes. But essentially, a mechanism says, I don't just want to know what the products were and what the reactants were. I want to know why what is going on in between. How do I get from reactants to products? What are the steps that go on? And those steps are important because they often determine what the actual products are going to be, where something is going to attach on a chain. Oftentimes relies on the mechanism and how it happens. So mechanism is basically how it is the process by which the reaction occurs. For us in halogenation, halogenation is going to occur by the formation of free radicals. Now you may be saying to yourself, you mean like political radicals? And of course not. What we're talking about here are chemical radicals, and so we're going to talk about what those are. So there's 3 steps, okay? So just keep in mind you got 3 steps here for a free radical chain mechanism. And the first step is what we call the initiation step. And this one's really easy. It doesn't actually involve the alkane at all. Basically, we got to break the chlorine molecule into 2 parts. So we said that's what the sunlight or some sort of light in the reaction is going to do. It's going to break the chlorine molecule into 2 chlorine atoms. Okay, now, what you may notice here is, of course, they've each got their 7 valence electrons. Not real pleased with that. They're not terribly stable at that point. They really want to react. Chlorine is pretty darn reactive, so it's going to want to react pretty quickly. And so that's going to be our next step. The next step is called propagation. And here's what goes on in the propagation step. So in propagation, what we want then is we want to be able to add this chlorine, and basically we want to be able to add the chlorine to our alkane. Now the way that that's going to work is that one of the chlorines is actually going to pull off a hydrogen, and it's going to create right here a free radical. Now basically a free radical in chemistry is something that has an extra unpaired electron, and that's a relatively unstable state. That's why I say in your body you want to take stuff like antioxidants to help react with that so that you don't have these free radicals running around in your body. And so these free radicals really want to react. And so via that first step there, where we're going to break off, and now the way this works is if you remember your electron nomenclature here, basically one electron is going to come from this bond, the other electron is going to be the one from the chlorine. Those are going to form this bond right here, okay? And then the other electron in the bond, because remember this is a fish hook, one electron, that's what's left over and leaves us as a free radical. So the next part of the propagation, and we're still in the propagation step here, the next part of that is another chlorine molecule is hanging out there. That is then going to react with our free radical, okay? And essentially the same basic thing that happened above is going to happen here. One electron is going to get donated here, one is going to get donated here. That's going to lead to this bond, and then what do we have free here? We've got another one of these guys. Now, what you can imagine, and this is the chain part of the chain mechanism, is that since this second propagation part here generated another chlorine atom, that we can sort of go back to this step right here, okay? Go back here, and it keeps going. Okay, and so that's going to keep going. That's a propagation step. It's a self-propagating reaction at this point. It's going to keep going. So it's going to keep going until when? Well, it's going to keep going until we get to a termination step. And in the termination step, basically what that means is you've got to get rid of the free radicals. You've got to get rid of the chlorine atoms. You've got to get rid of the free radicals. And so there's kind of three ways that this can happen. The chlorine atoms themselves can react with each other to form sort of their normal everyday chlorine molecule. Okay. Two of the free radicals can actually come together. Now that obviously is going to lead us with a product that was somewhat unexpected, and so of course we're going to have to alter the conditions of the reaction to get that, but that's not really what we're looking for. Or we can just stop by, we can add one of those chlorine atoms onto the alkyl radical, which is what we want, and so that's going to lead to the desired product that we were sort of looking for. So that will help to end a chain. And then if we get some of those chlorine molecules to react with each other, that will be the other part of the termination step. Okay, a lot of stuff there, guys. Kind of our first time seeing mechanisms, so hopefully it's not too terribly confusing. We're going to see a lot more of them later. And again, don't panic. We're not going to talk about anything too massively difficult, but we are going to work through some problems where we're going to practice doing these free radical chain mechanisms. What I would recommend is sort of a practice for yourself is to, on your own paper, see if you can duplicate the same process, but with bromine, with Br2, okay, instead of the chlorine, just to see if you can spell the process out for yourself. All right, thanks a lot, guys.